Hello, good morning, ladies and gentlemen. It's very excited to welcome you to this morning's webinar and online demo, jointly organized by Bruker, Crest Nano Systems, and Monash University. My name is Li Yang, and I will be your host today for this section, Piezo material characterization techniques and atomic force microscopy. So we have an exciting program lined up for you today. On the agenda, it will first start with a talk from our invited speaker, Dr. Chang Wei-Si, head of Nano-Analytical Platform from Monash University, Malaysia. She will be presenting an overview of piezo material and its application in piezo material studies. This will then followed by Dr. Chen Yun, who is Bruker's application scientist. He will give us a talk on the recent advanced atomic force microscopy and its application in piezo material studies. This will start around 10:45 a.m. Followed by this part two of the program. It will be an online demonstration sections by using the Bruker dimension icon system. So after that, it will be the Q&A sections. Should be around 12 noon. So the whole program should conclude by 12:15 p.m. Just in time for lunch for everyone. So before we commence, I want to share that all the attendees will be put on listen-only modes. But there is a opportunity where you can actually interact with the speakers or with us through the Q&A panel. So there is a panel on your right-hand side where you can key in your questions. We will collect all the questions and get the speakers to discuss with you at the end of the section, meaning that after the demonstration sections. All right, so without further ado, let me introduce our first speaker today, Dr. Chang Wei-Si. Dr. Chang is a senior lecturer at the School of Engineering and head of Nano Analytical Platform NAD from Monash University, Malaysia. Her research interests focus on functional oxide thin film and the nanostructures, especially on piezoelectric, ferroelectric, or multi-ferro for energy application to achieve clean energy and the sustainable development, so on. Dr. Chang is actually a high achiever who has been received multiple awards from AOF SRR Japan and the Sharon Award to Taiwan National Science Council Postdoctoral Fellowship Award from 2012 to 2013. She's also an associated fellow at the Institute of Microengineering and Microelectronics at UKM since 2015, and the adjunct associate professor of the Department of Mechanical Engineering and the Research Center for Intelligent Medical Devices at Mingchi University of Technology in Taiwan since 2 years back. Dr. Chang was also the visiting scholar in SSLEEC at Uni California, Santa Barbara from July to December 2018. And last year, she was selected as a member of the Young Scientist Network Academic for Science Malaysia. This year, she joined the Journal of American Ceramic Society as an associate editor. So we now invite Dr. Chang to share with us an overview of piezo material and its application in piezo material studies. Dr. Chang.
Thank you, Li Yang. Thank you for your introduction. Hello, everyone. Even though we cannot meet face to face, but I hope that you will enjoy throughout this entire session, about 2-hour session. First, I would like to thank Bruker Nanosurface and Crest Nano Solution for inviting me to this platform and to have the opportunity to give a presentation and discuss on the piezo-response force microscopy. This is a very important analytical tool by now. Today, the topics that I would like to focus is on piezo force response microscopy in functional materials. And of course, I'm excited to be here, and I hope you will be excited as me, right? So we will begin with the history of the PFM. Now, in 1992, Gardner and Dransfeld detected polarized regions in ferroelectric called polymer film that is based on converse piezoelectric effect. So this is the first approach that Gardner and Dransfeld used to detect the polarized regions in a ferroelectric materials, which is based on converse piezoelectric effect. Although the invention of this PFM is very much related to the advances in ferroelectricity in the 90s, it did not quickly become the key analytical tool for several years, simply because during that time, the scaling behavior is not at the nanoscale behavior. So when the scaling behavior of ferroelectric, that is, we talk about the miniaturization, we talk about the nanoscale behavior, is at the forefront of scientific studies. Now, PFM has become the mainstream imaging and analytical tool for ferroelectric and piezoelectric materials. So nowadays, the functional materials that has polarity, that consists of ferroelectric and piezoelectric material characteristic will be used PFM as an analytical tool to study the localized nanoscale behavior of the materials. So we take a look at the application of PFM. What can PFM do for us? So from here we can see that the PFM allows us to do domain imaging, not only topography, but domain imaging, domain writing. You can actually provide an electric bias to your material. That is what we call domain writing. And domain dynamics and evolution, spectroscopy, mapping and switching, hysteresis load of your material, that is through PFM spectroscopy, to differentiate an active grain and inactive grain. So typically for these kind of materials, it's a ferroelectric materials. That is why you can see a hysteresis curve in the PFM spectroscopy. And it also allows you to measure the temperature dynamics and phase transition of your material. So this is what the PFM can do and to measure the behavior of your materials. So now the potential of the PFM is broad because it can be utilized in ultra-thin epitaxial films, nanoscale capacitors, nanotubes, bulk single crystal, and bulk ceramic. So it means the PFM can cover a very broad range in terms of the dimension, sub-micrometer dimension of the materials. And that is why until now, it has become a very important analytical tool for us to understand the electrical behavior, mechanical behavior of the materials. So let's take a look at this piezoelectric effect. So the piezoelectric basically rely on a certain of materials that were subjected to mechanical strain that became electrical polarized. And the degree of polarization was proportional to the applied strain. And in this case, if you look at a material that able to convert mechanical strain to electrically polarized, so it's vice versa as well, meaning the mechanical and electrical energy is sort of electromechanical coupling factor. So you can actually provide a mechanical stress to generate polarization, charges, or current from the material. Or alternatively, you can actually provide electric field to your material and lead to a sort of a displacement and therefore strain being generated in your material. So this kind of material is very, very important in many of the applications, because the mechanical and electrical energy conversion, which is termed as electromechanical coupling factor, has been used in variety area. For example, you can find it in medical devices, you can find it in the MEMS, and a lot of devices that is related to the energy conversion and energy harvesting. So typically, the piezoelectric behavior can be grouped into two distinct groups. So the first is direct piezoelectric effect. And in this, the direct piezoelectric effect indicates the contraction and the expansion of a material will give rise to the electrical response. And you can see from here, based on the equations, the expression of it, we can see the relation between charge and strain, as well as the piezoelectric coefficients, which is the material's property. And the second is converse piezoelectric effect. In converse piezoelectric effect, the mechanical response to electrical stimulation. And that is when a piezoelectric material placed in an electric field, the material becomes strained. And you can see this is what is happening here. And this is given the expression for the converse piezoelectric effect. And this would be the materials that consist of the piezo and ferroelectric behavior. To exhibit piezoelectricity, right? This is what we have seen here. The structure of a material should have no center of symmetry. That's why you can see this small little atom is actually shifted from the center, shifted away from the center if you are looking at this sort of a cubic form. So the shifted of these atoms indicate that these material have no center of symmetry. And if you look at the relation between the piezoelectric and ferroelectric materials in this picture, the ferroelectric is a subgroup of piezoelectric materials. So what does it mean? It means not all piezoelectric material is ferroelectric material, but all ferroelectric consists of the behavior of piezoelectric. Now, in this case, both piezo and ferroelectric will have charges and, of course, piezoelectricity. But ferroelectric will have an extra characteristic, that is, it's allowed to possess spontaneous polarization, which can be permanently switched upon applied electric field. And that is why we say that ferroelectric material is consists of all the behavior of piezoelectric material, but not all piezoelectric is ferroelectric. The difference is the spontaneous polarization. And having all these characteristics, if you have a charges, piezoelectricity, ferroelectricity, and it allows you to make the material for energy harvesting. That is, we are looking into the energy conversion mechanism, and these materials are prone to sensors and actuators for medical, microelectronics application, and as well as the other key issues that we need to understand. What is the operating environment of these materials in order for it to continue with the duty in terms of the sustainability and continuation of the sensing's potential. So here we have a look at this PFM setup. Because of all these capabilities in the materials, we are interested to find out in terms of the behavior, characteristic, electrical characteristic behavior from these functional materials, for example, piezoelectric and ferroelectric materials. So PFM is so far by far the only tools that can actually offer us to study the electromechanical behavior in these materials. So what actually PFM can help us to analyze? In PFM setup, in here, this is a very simple PFM setup. It shows an AC voltage between a tip and a sample that can apply between the tip and a sample. Of course, the tip has to be conductive. All right, when you are using a PFM measurement, you need to select the tip, a conductive tip. So having a conductive tip, it will act as a movable top electrode that couple to the material surface. So the vertical surface strain, in this case, that is the Z direction, typically named as the Z directions, will be shown as amplitude. That will actually measure the change of your material dimension, which is in Z direction, the strain along Z direction. And the phase indicates the polarization direction. So if you look at the materials, you can see two phenomena. The first is the expansion and contraction of your material. The second is the polarization direction. On the left is indicate a polarization upward, and on the right is downward. So this information will be captured by PFM. If you are using a PFM to measure, to understand the change, the displacement, the change in the polarization, the domain orientation. So such a measurement is referred to out of plane measurement, because in this case, you are having the direction of the measurement is parallel with C direction, and that is what we call OOP, out of plane direction, out of plane measurement. So if these measurements can also be subjected to the change of temperature, the change of electric field, light, and also able to measure under liquid environment. So if you really wanted to understand how your material will behave in these operating environment, you can try, and I believe Bruker multi-mode AFM have this temperature that can offer up to 250 degrees Celsius. And for the electric field, can goes up to positive and negative 10 volt bias. So we have actually mentioned the vertical measurement, that is the OOP. How about in the lateral orientation? So on the left, referring to vertical PFM, that basically will provide you the measurement along Z directions. So if your domains in your material is lying along a lateral orientation that is shown in C and D figures, what it will generate is a shear movement in your material, and your cantilever basically will exhibit a torsion in response to the shear movement in your material, and it will produce a 2D imaging, indicate the in plane, that is what we call IP domain orientation. So maybe we can have a look at this, one of the examples. This is the in plane PFM images measured on a BFO film of varying thickness. You can see the thickness ranging from 120 nanometer to 2 nanometer. So the three different tones, as you can see from the images here, consist of white, black, and brown. So a brown and a very dark, we actually name it as black. then these actually correspond to 4 variants because bismuth ferrite has the 4 variants of polarization directions. So under this measurement, it allows us to see the different contrasts, and these different contrasts typically indicate the orientation of the domain. And typically, if you combine this in-plane orientation or information that you obtain from PFM with the C-plane, that is the XRD result, it allows you to study the whole BFO phase structure. It's a kind of complete study by looking into the 3-dimension phase structure. So based on this, we will be able to understand that this is actually a distorted rhombohedral structure. And if you look at the in-plane information, the film is actually deposited on 2 different substrates. One is the STO and the other is the SO. All right, so what you can see from here, the C plane will show a slightly difference, and also the in plane will show a different contrast as well, but ultimately it leads to a conclusion that is a rhombohedral distorted structure. And we can also use PFM for domain writing. What is exactly shown in this paper is that the relaxation evolution of BFO domains created by pulse voltages, because PFM have a range of electric field which range from positive and negative 10 volts, and by applying these pulse voltages to it, you will see 2 distinct different. One is the bright and the other is a dark contrast, and these typically correspond to a polarization upward and downward. So therefore, on your left is indicate a polarization upward, means the bright color indicate a polarization upward in your material, whereas on the left is polarization downward, polarization downwards because of the applied field to the materials. And this will help us to understand the role of surface charges in the materials. So I think PFM allows us to do a lot of things to understand our material in depth. So what is domain writing? If you can see from here, a very simple schematic is that originally this is your material which you haven't provided any of the electric field or applied bias to the material. So when you put this material for under PFM and you apply, say, a negative 10 volts into this region, a smaller region within the large region. Say the large region is 5 by 5. Now you are offering a domain writing by providing a negative 10 volts within the region 3 by 3. So you will see that this region will have a result in a contrast form compared to the original view. And again, if you want to apply a small region, say 1 by 1, with typically positive 10 volts, and this will also lead to a change in the polarization. And so here is a very obvious distinct polarization directions that you can see from the cross-section view, because polarization is having a charges. It will interact with the voltage bias that you apply to it, and that is how you can actually analyze the polarized response of your materials, and therefore the surface charges that accumulate on your material surface. So this is how the PFM can perform in terms of the domain writing. In my group, we use a lot PFM as an analytical tool, and we study piezo ferroelectric materials. And what we use the PFM as an analytical tool is we wanted to understand the effect of light as well as the applied electric field. Remember just now I showed you that the PFM can actually apply a range of bias from positive to negative 10 volt. So we are making use of these tip bias voltage from PFM, and we applied to the material, to piezo ferroelectric material, and to observe the change in polarization as well as strain, in order to understand how it will affect photoactivity as well as photoelectrochemical activity. It's sort of like a combination of polarization dependent chemical reactivity in this case, and how the strain and polarization will react when you have the external source, for example, light and applied field, and ultimately lead to the application in photoactivity and the PEC activity. So this is what I'm going to share with you, what my group has been doing and how we make use of the PFM tool to help us further understand the material behavior and to explore further the potential of the materials in this application. So here we have two different materials. One is a BFO, another is a ND-doped BFO. This is a thin film, and we want to study this material in response to photoelectrochemical activity. And we understand that a BFO is a highly leakage material. It's already reported vice versa. And so we use our PFM to analyze the phase. And we sort of found that BNFO, that is an ND-doped BFO, has a very wide area in the hysteresis lobe compared to BFO. And how would this able to contribute to the PEC activity? Knowing that having this wide area, we assume that it actually definitely reduces the leakage, reduce the potential leakage. And we check the current density in terms of the stability, and we found that BNFO, the BFO with doped ND, indeed is having much stable response compared to BFO. And in terms of the IPC conversion, BNFO behaved much better. So judging from here, by knowing these, we can actually explore a lot from here to help us to understand the behavior of the BNFO in photoelectrochemical activity, indicate that having the ND dopants, it eliminates the trapped states and reduce the charge recombination. So this is how we make use of the analytical tool PFM to move further on for materials selections. And the second one is that we try to understand how polarization can actually affect the response in terms of the PEC activity by having a PR. So you can see on your very right, this figure it's indicating PR, polarization up, because we applied a electric field and we measure under the PFM. It shows it's a polarization upward, in which the sample area, which is a 5 by 5, show majority have a PR orientation, whereas the bottom is P down, polarization down, all right? And this has to be, depends on what is the objective of your measurement. For this case, we applied the electric field to the materials in order to tune the polarization direction, purposely tune to P up and P down. And we want to see the interactions of the polarization, how it can affect the flows of electron due to the band bending between the BFO and the liquid interface. So we can have a better understanding by showing here is that P up will lead to a downward band bending, and this downward band bending will create an easier path for the flow of electrons, whereas P down will generate an upward band bending. And this outward band bending will require a higher potential barrier for the flows of the electrons to overcome. And this can be proven from this electrode current that we have measured here, indicating that indeed there is downward band bending and outward band bending that control the flow of electrons. And of all this actually is affected by the polarization directions. So imagine if you have a materials with an internal internal charges with a polarization direction clearly distinct, you should know which of the material you should choose in order to have an easier flow path. And the next is we make use of this PFM to study gallium nitride. And for this, we would like to understand the photoactivity behavior, how this will lead to the photoactivity behavior in gallium nitride. We understand that GaN is a very common material in LED and the micro LED as well. So we try to compare GaN materials with in-GaN materials, and we are looking at the strain behavior as a response of light. So we understand that GaN nitride is not a ferroelectric, but it is a very, very good piezoelectric materials because it has a very high D33 coefficients. That's a piezoelectric coefficients. So we are using a light source to excite GaN, and we can see the response from here. If it is off, so the amplitude will be somewhere around 20 to 22 the picometer, but if it is being exposed to light, it will have a jump. All right, so this is a behavior in terms of to study the strain behavior of GaN. So if you look at the interface between GaN and in-GaN, it actually able to double up the strain behavior in response to light. So this will also lead us to further understand the strain activity in GaN materials when it's being exposed to light, and when it's being to ultimately how it will actually affect LED application as well as solar cell. So the next will be bismuth ferrite ceramic. So far, I have shown quite a number of examples in the thin film. This is the first ceramic examples that I actually would like to share with you by using PFM analytical tool. But here we show a combination of PFM and KPFM. Not only we use PFM, but we need to couple with PFM to show the evidence. So in PFM, we have poked the sample by providing a domain writing, and you can see it is a very different compared to the pristine sample. So on the left is the phase, the change of the polarization, and on the right is amplitude imaging that will show you the change in the strain or the materials displacement, judging from the images that we have seen here by applying a 10 volts bias. And how about providing a light illumination? So it also shows that it will affect the polarization as well as the strain behavior in the materials. So PFM is able to detect the changes from the two external sources, that is the electric field as well as the light. And it is very obvious in KPFM in terms of illumination, in which compared to the one that has been applied with the plus minus 10 volt bias. So we have the graph shown here. This is also obtained from PFM, indicate in which the piezoelectric coefficients can be induced by 6% with light illumination, and the voltage, that is the coercive field voltage, can also be increased by 20% based on the PFM2 measurements. So the sample here shows that it is a 7% ND-doped BFO ceramic, and this is a very important information. Supposingly, you are using the materials for photovoltaic applications and for other sensors and actuator devices. How would you like to enhance your materials by the external sources? This might be informations, very good informations for the engineers to select the materials for the right application. And moving from here is another type of a bismuth ferrite ceramic. It's an SM and MN called BFO, and we use PFM2 to study the this material, and we actually able to provide a 2D image, and this is a OOP orientation. And what we see that we are looking into 4 points here. There's point 1, 2, 3, 4. That means we are doing a localized region, and for each of this individual region, we obtain the hysteresis curve and also the correspond amplitude information. There's a strain information as well. So what we are trying to show here is that PFM2 is able to help us to look into a very detailed information, especially the localized region, in the case that each of these could have a different behavior. For example, in terms of the hysteresis slope, you can see from 1 to 0.4, the behavior is different in terms of the ferroelectricity as well as the piezoelectricity as well. We further increase the temperature on the same material, and then we can see the distinct behavior with the change of temperature. So there is a drastic change in the IP. So for information, these are all in-plane phase contrast. So in the in-plane phase contrast, we can see at 175 degrees Celsius, that is, judging from here, we can see 175 degrees Celsius is showing drastic phase transition by the temperature dependent parameters. So here is indicating that not only you can understand the in-plane orientation, you can also understand the OOP informations, obtain OOP informations from your materials. This is another BFO, and another results to show by comparing a BFO versus a BFO 7% antidote. This is to show that how important to have this PFM analytical tool to identify the behavior of the materials, because we can see this is BFO has a very huge leakage, and that is why the behavior of the hysteresis slope and as well as the amplitude is different compared to 7ND. And 7ND having this is also indicate that the leakage has been improved. All right. We also make use of the X-ray absorption spectra to prove the behavior of the observations that we've seen in PFM2. And for this, another example, that is a bismuth hafnium, and we use these to study the phase transition or phase structure of a different composition of hafnium. And what we found that it will be able to change from ferroelectric to relaxer based on the step-by-step changes, measurements for the both materials. So we can see that this 25% dope hafnium into BFO will have the combination of a relaxer behavior in the materials, whereas with only 5% dope hafnium, we have a pure ferroelectric behavior in the materials. And this is again combined with XRD study to obtain the phase percentage change and be able to correlate well with our PFM tool. So with this, nowadays, until now, the advances in PFM is covering a lot. It's not only a vertical PFM that I have shown, but it also includes switching spectroscopy PFM, stroboscopic PFM, resonant enhanced PFM, metrological PFM, and band excitation PFM. The key issue here is when you want to use a PFM to measure your sample or your material, it is important for you to understand what are the properties that is to your own interest or what you want to measure. Then only you select the right PFM to the right mode for you to measure. If you are interested in terms of the electrical, electromechanical properties, most likely a vector PFM will be good enough for you to measure. And the other important information is what will be the operating environment that you really want to study. For example, temperature, electric field, and liquid or light. So you need to provide these external source to excite your material so that it can be captured by the PFM. It's important for you to understand your material before you go to measure under PFM too, so that you won't be able to comment how come I won't be able to obtain information from PFM too. So first of all, you need to understand your material before using PFM too. This is a very important message. And also the other thing is the tip selections is also important because first, not only the conductive tip, but the type of the conductive layer is also a key criteria that how it will be able to respond to the charges, because all is about the resolution, the sensitivity, and what is the your expectation of this imaging tool. So with this, I would like to thank my team because they have done a lot of hard work to obtain this data. And I would like to thank everyone for this talk. Thank you.
Thank you, Dr. Chang, for the very comprehensive and informative sections. I guess the audience must have some questions by now, which we received some already. So based on the arrangement, if anyone have further questions, please feel free to type in the question or chat panel. We will all discuss this together at the end of today's sections. So let me now invite our second speaker today, which is Dr. Chen Yun, to share with us on the recent advance atomic force microscopy and its application in piezo material studies. Dr. Chen works as an application scientist at Bruker Nanosurface Divisions, focused on exploring application and providing technical support of surface metrology and tribology instruments. He was academically trained in biomedical engineering, biotechnology, and physical chemistries, and has more than 10 years of experience in various applications of AFM, including the nanomechanical and nanoelectrical characterizations of materials. Dr. Chen, please.
Thanks, Leon. Thanks for Dr. Chang's very nice and detailed presentation. I think the audience already get a very nice idea about the piezo materials and how to characterize them with atomic force microscopy. So I will, in composition, I will just briefly first go through some basics as a quick recap for the piezoelectricity. So I think Dr. Chang almost covered everything already, so just a quick recap. So why we have the piezo materials? We all know that it's discovered over a century ago, back in 1880s. So the piezo materials basically show that once you press it, it generates the bias difference through the whole material body. So why we have this. If we look into the crystal orientation or crystal structure, then we know that we have in total 32 points systems, right? And out of these 32, we have central symmetric point systems, point groups, and also non-central symmetrics. So if it's a material, the crystal is central symmetric, of course, we don't expect to see any piezo response because in all the directions it's the same. So of course you don't have the polarization. And even for the non-central symmetric point groups, you still have one exception, like this 432, which will not present any piezo materials from the theory. So that gives only 21 left over. And we know that out of all the materials we have right now, probably it's over a million or something like that. So only about 30% is non-central symmetrics. And out of this 30% of all materials, only a few hundreds by now, we discover we have the piezoelectric responses. Actually, still quite a lot because some common material like our fingernails and like our teeth, also the silk fibers, all these materials have been reported to have the piezo response. So again, if we check from the crystal structure, we understand why this kind of material will have the piezo response, and why when we apply electric field, it will have the polarization, rearrangement, things like that. And also, we as Dr. Chen already mentioned, sometimes we also have to consider the temperature. You all know the definition of the Curie temperature, right? So when the temperature is higher than Curie temperature, basically the structure is going to be central symmetric. You lose the piezoelectricity. While the temperature is lower than the Curie temperature, you still possess this kind of polarized structure. So you can have the piezoelectricity. So that's from the crystal structure. But we all know that to have the single crystal material, it will be very expensive, and sometimes it's very difficult to manufacture and produce. So it's quite common in the piezo material applications, we see it's the ceramic materials instead of single crystal materials. But one thing about the ceramic is that the orientation of the grains is basically random. So as the scheme showing you here, all the grains here shows different orientations, which in total, if it's completely random, statically speaking, it will be 0. You won't have any piezoelectric response. So how to make this material useful, or this kind of ceramic material useful, or give a stronger piezoelectric response? We can do the polling. I think Dr. Chang also mentioned that. Polling means when we apply an electric field strong enough to polarize all the domains in the same direction, then afterwards, if most of the polarization can be remained, then we have this kind of very strong piezoelectricity in this direction. So this is how actually in practice, how we manufacture the piezoelectric materials as ceramic materials. Then the question is, okay, we now have this kind of materials, how can we characterize it? So at the discovery of the piezoelectrical behaviors, actually people notice as a direct piezoelectric material response, which is when you apply a pressure, compression, or some stress onto the sample, then you will see the bias change. Actually, that's also why we have this name. This piezoelectricity is actually related to the Latin language, right? So the Piezo electron, which Piezo in Latin means compression and stress. So that's actually very straightforward to understand. It's a conversion between the mechanical and the electrical responses. And the second group is actually more important in today's topic in PFM, because most of the time when we do the PFM, we are actually looking to the converse piezo response, which we apply bias through the material body, then observe the deformation, dimensional deformation of the material. So this is usually how we do a PFM. And the third group is the shearing, which means your polarization and your electric field direction is different than the mechanical deformation. So that's can also be detected from the PFM. So I think I don't need to stress out how the piezoelectric material is important as functional materials nowadays. It's quite widely used in all kinds of nanoelectric measurement, nanoelectric device, and also in thin films and the energy harvesting, perovskite materials, all these kinds of things. Even the biomedical application, nowadays people look into the piezo material as well. So later on, I will have specific examples in different fields to show this kind of potential application for this group of materials. And another thing important in quantify or characterize the piezoelectric materials is this coefficient, right? The unit of this coefficient depends on which kind of response we're talking about, whether it's a direct piezoelectrical response or it's a converse one. So the unit can be different. But nevertheless, the definition of this coefficient is always the same. So let's say we have this kind of polarization and in relationship to our strain or stress here, strain. So we have this matrix for the coefficient. And each part actually stands for in certain orientation, what is the coefficient it is. And the definition sometimes can be confusing. I think for 1, 2, 3 is quite straightforward. It's X, Y, Z, right? And sometimes we also have this 4, 5, 6, which sometimes people find it's difficult to memorize. The easy way to memorize it is for 4, actually, you are looking to the response in the YZ plane without 1. So that's usually how I memorize it. And for 5 is without 2, so it's in the 1, 3 plane, looking to the response. So nevertheless, no matter how you define this coefficient, for most of the piezo materials, this response is quite small. Especially when nowadays it's quite popular to have the thin film piezo materials applications, where the response will be even lower. Let's take the example of the PZT, which consider a quite strong piezoelectric materials. Even for the PZT, when you have you just see the simple deduction here. If we consider the D33 is 370 picometer per volt, and when we apply a 1 volt following the same direction, then the deformation actually is only about 40 angstroms, which means it's sub-nanometers. Such kind of small deformation can be quite difficult to detect, which actually pose a very important question to the. Sorry for the background noise. I'm in the demo lab right now, so our pumps are running from time to time. It will stop very soon anyway. So in a traditional way to characterize the piezoelectric response, we actually, as Dr. Chang mentioned earlier, we can just press the material and measure the voltage change. But again, when it comes to the thin film, this kind of response can be quite small. So the traditional quasi-static method can be sometimes very difficult to be carried out. And of course, we can also use dynamic resonance method. In the previous equation, we see that your D33 is related to the dielectric coefficient of the material. So by using the ionometer or things like that, we can use dynamic resonance method to measure the dielectric material. And from there, we get the piezoelectric coefficient. And we can also use a laser interferometry method to detect the deformation of the material when you apply the bounce, which again, we are actually measuring the converse piezoelectric response. And the above three ones are the quantitative method people usually use for the bunker material, piezo materials. And there are some other qualitative methods as well. Most of them actually related to the optical method, need the help from optical method. For example, we can have the EC approach because different grains with different orientations will respond differently when you put it in the EC environment. And the optical properties of these grains with different orientation will also be different. So we can also use a light scattering approach to see the orientation distribution over the material, and so far so forth. But as we said, so no matter for the quantitative and the qualitative method for the mass or the large material box, they may not fit when we are talking about the thin film applications. So first of all, we need the higher sensitivity. As we just discussed, the piezo response from thin film can be quite weak. So we really need this kind of Z sensitivity to measure this kind of small deformation. And second, we need a better lateral resolution. Again, when we are talking about ceramic materials, we have different grains. And there are loads of literature talking about how the interface, or we call the domain walls, are important for the piezo response for this kind of materials and their applications. So in order to review this kind of grain boundary or domain boundaries, we really need very high lateral resolution, which the normal optical method cannot provide. And another advantage of using the AFM for the piezo response measurement is AFM can be, it's actually plays as a platform. So you can have all different kinds of modes integrate onto this platform. For example, besides the piezo response, we can in situ measure the mechanical response and other nanoelectrical response, things like that. So doing the PFM in atomic force microscopy can really give you the full spectrum material characterization. So I'm not sure how many of you are actually familiar with AFM. So AFM may look quite different, but their basic components are always the same. So AFM is a touch method. So you always have a tip to touch your sample, no matter which mode you use. So the tip can sense the sample topography, then respond to the tip deflection, and the controller will, based on this deflection, give the feedback of the XYZ directions, how to move up and down, and how to do the scanning in the XY planes. From there, we get the topography of the surface. And of course, we also need the interface between the controller and the user, because the user don't understand the voltage signals from the controller. So we need an interface. So these are the four basic components for AFM: the probe, the scanner, the controller, and the software. So specifically for PFM, thanks again to Dr. Chang. She already mentioned the working principle of the PFM. So as I said, most of the time in PFM, we are measuring the converse piezoelectric response. So we apply the bias to the sample and monitor the deformation of the sample. But this kind of, if we just use a DC bias, this response is very small. We mentioned earlier, even for PZT, which is relatively strong piezo material, this kind of deformation can be sub-nanometers. So in order to make this kind of mechanical response stronger or easy to detect, we can use different approaches. So the first one, or the most common one, is we apply AC instead of DC signals. So under this AC field, electric field, the deformation, mechanical deformation of the materials also following these AC patterns. And this AC signal, we can use the locking amplifier to extract from it and demodulate. From the amplitude and phase, we can know the piezo response strength and the piezo response orientation, or the piezo grain orientation, or the polarization direction, depends on what kind of material you're talking about. So this is the basic working principle of the PFM. Of course, nowadays there are a few developments in the traditional PFM method to further boost the signals or to screen out the non-piezo electrical responses, like the electrostatic interactions, things like that, which commonly coupled into the piezo response. So this one we have some slides to mention later on. So from the PFM, of course, we can get the image because AFM is originally it's an imaging tool. From there, we can also get the dynamic piezo response plot, or the butterfly curve. I think you all know about it. From this kind of butterfly curve or the hysteresis loop of a specific material, we can further derive a lot of important index to define or characterize these materials. So for example, we can have the cohesive bias, we can have the imprint, we can have the remnant polarization, things like that by fitting the hysteresis loop. So these are just a quick cap about PFM and its physical backgrounds. So in the following slides, I'm going to share some applications from literatures using our system to perform PFM for the different kinds of applications. This example is important application in the flexible device. So the material is a PVDF, which is quite commonly used nowadays. So in order to be applied into the flexible device, of course, you want your film to be as thin as possible. But in the meanwhile, we still want to maintain the piezoelectric properties of the film. So in this paper, the authors actually looking into the piezo response versus film thickness to see how many layers I can still have enough piezo response, so which can be still useful in my application. I think earlier in Dr. Chang's presentation, she also mentioned some similar applications to look into the piezo response versus film thickness. So this is just a quick example. And what I want to emphasize here is that we already mentioned for thin film, basically we need a very high sensitivity to detect the piezo response. For such kind of application, specifically, you really need a very, very sensitive PFM to detect this single layer piezo response. So that's why the AFM can be really useful in this application. So the previous example showing you the Z sensitivity or Z resolution. And this example actually showing you the lateral resolution. So if you still remember a couple of slides before, I mentioned there are some new requests why people moving from the traditional characterization tools to the PFM for the characterization of the piezoelectric materials. So the first one we mentioned is the Z sensitivity, and the second one will be the lateral sensitivity. So this application is using the piezoelectric materials in the new generation of memories. And in this way, we use the domain walls as a the domain walls plays a very important role in the switching of the memory or the storage information, writing the information from memory. So people here looking to the domain wall use PFM. The resolution here is really about a few tens of nanometers, which is directly related to the tip radius. For the normal AFM tips, the tip radius can be as sharp as a couple nanometers. But we previously mentioned that for PFM, you always need a conductive tip, which the tip radius will be bigger because of the conductive coatings. So here you can see the lateral resolution is about 10 nanometers, something like that, which is just limited by the tip radius. So it's hard to imagine with other techniques you can really resolve this kind of fine features with this kind of lateral dimensions. So again, this one proves what kind of lateral resolution we can achieve with PFM. So the take-home message is it's directly related to tip radius. If you can, in the future, let's say, you can have very sharp tips, still conductive. Actually, it's already existing in the market. The lateral resolution can be even better. And another important field in the current piezo material study is 2D materials. So it's still quite a hot topic or a lot of arguments in the field. What kind of 2D material can really possess a piezo response? Or are we really seeing the true piezo response or something else? But nevertheless, it's quite common to observe when you stack different layers of the 2D materials together, you will have the piezo response in many materials. For example, here we are showing the F-indium selenium, which is a common material nowadays for 2D and piezoelectric studies. This is published from the AUS using our ICON system. You can see from the topography, we have this 2D material flake. This one is relatively thick. And if we do the PFM on this flake, we can see that it possesses both in-plane and out-of-plane responses, which some people call it out-plane, in-plane. Sometimes you call it lateral, horizontal, lateral or vertical. It depends on how you define. But nevertheless, it's clear that you have different orientation within this flake, very likely due to the thickness of this flake. So different thickness means you have different numbers of layers underneath. So we know that for sure, how many layers of these 2D materials definitely change your piezo response or orientation inside. And also the alignment between these different layers also affect the piezo response. So this is just a quick example about the 2D materials and the piezoelectric materials studies. Again, since it's very thin and so the 2D materials generally is very thin, right? The flake we are seeing here is quite thick. But there are literatures talking about other 2D materials with single layer or double layer, you still observe PFM. There, you really need a very high sensitivity in Z direction to detect this kind of response. So another example is showing you that how to combine different kinds of nanoelectrical, nanomechanical modes together with PFM to give you the full spectrum material characterization on the AFM platform. This is a perovskite material here, and clearly from the topography we see the different grains separate nicely. And from the PFM, here we actually looking to the in-plane PFM response. So you can see even within different grains, you have many domains distributed over the whole grains, which tells you that actually the domain distribution within a single grain is not homogeneous. And the same thing, actually, we notice that the domain distribution for this specific grain is slightly different from the other one. Specifically, this domain in this grain is actually wider than the other one. Then if we combine it with the KPFM, which detects surface potential of the material, we can see that from the KPFM, we also see this kind of distribution, which give you an idea or give you some basic experiment observation, how to understand this kind of materials. Actually, if you combine this kind of observation with EBSD, you will see that the crystal orientation of this grain is also different from the rest of the grains. So if you combine these things together, you can have a full picture of how this kind of piezo electric domains distribution in specific grains, and how this kind of different grains may have different kind of nanoelectric properties over the whole materials. So this is just a very nice example to show you how to combine all different kind of modes of AFM, and also together with other technology to fully understand the material behaviors. And I mentioned earlier that it's not only about nanoelectrical applications. People also look into the application of piezo response materials in biomedical field. So here is a quick example. So I'm not sure if you have any backgrounds in the cell culture, incubation, things like that. But the basic idea is that cell can respond to the substrate it grows and it's incubated, and develop into different kind of destinations. For example, our stem cells, when you change the incubation substrate with different patterns or with different stiffness, the stem cell can actually develop into different kind of body cells. So people thinking about using the piezo electric material, which can be used to induce different kind of electrical and mechanical stimulus to the cell. And from there, we can see how this kind of stimulus actually direct the cell development. So that's why people look into the piezo material application in this field. But the traditional piezo material, especially the piezo material ceramics, these are too stiff for cell incubations. So then we have to look into some softer material together with the biocompatibility, which give us this kind of a new generation of the piezo electro materials. Quite often there are some polymers together with some copolymers materials. So again, here we use different kind of AFM modes. First, we want to understand the mechanical property of these materials. It needs to be soft, relatively soft, and it needs to be uniform, like that. And we can also look into the surface potential or other nanoelectrical properties of these materials. For example, what's the charge accumulation on the surface at the different kind of conditions. And last, we need to check the piezo response, whether this kind of pillar structure can give you enough piezo response so we can really efficiently induce this mechanical and electrical stimuli to the cell. So combine them together again. We are showing you that how to use AFM as fully equipped platform to perform different kind of material characterizations. And so in the following slide, I'm just give you a quick recap on the recent developments in the PFM specific for Bruker. So one thing is this data cube. So the data cube mode actually is at each pixel, you are holding the tip onto the surface. During this holding session, you can perform nanoelectro measurement, whether you ramp your DC sample bios, or in PFM, maybe we sweep the frequencies, or we ramp the AC amplitude or EC bios to see how the piezo response actually changed. So this why we call the data cube, because normal AFM give you a XY plane image, right, with the height or some other signals, current or mechanical properties. This is, but it's a 2D matrix. But in data cube, besides this 2D matrix, we have a third axis, which we can ramp our electrical signals. So that's actually give you a cube instead of the matrix. That's why we call it data cube. So how can we use it in specifically for PFM? We mentioned earlier many times the piezoelectric response from, especially from the thin film or the 2D materials, is very weak. Even if we use the locking amplifier, use the AC drive signal and detect the AC deformation, it may not be enough for some application. So people use the resonance enhance method to enhance the signal of this kind of deformation. But at different locations for material, the material's roughness can be different. And the material itself can also be not that homogeneous, which all give you the results that at each pixel or each location, the tip interaction with your sample can be quite different. The content model can be quite different. And this kind of different content model will change your resonance frequency at this specific location. So in the DataCube mode, I mentioned earlier, we can sweep the frequency. So by doing this, we can always make sure that we are collecting the piezo response at the strongest point, which is the contact resonance frequency at this specific pixel. So in this way, we guarantee that you always get the strongest PFM signal for the whole image. And of course, from the data we get, we can actually derive a lot of information other than the amplitude. For example, we can look into the mechanical properties, as we mentioned earlier. We can look into the additions. We can look into the frequency change for this contact resonance. And we can also look into the phase of at different locations under the contact resonance. So all this kind of information can be derived from a single scan. So it's really a lot of information to digest here. And this image just showing you how it give you the 3D concept of this data cube concept. So you have the XY, which is the usual AFM image plane. And in the Z direction, we have this kind of electro signal sweeping. In this case, we sweep the DC, then we at each different point of the DC, we have a separate image. When we combine them together, actually, it looks like a cube. So another important thing is about the switching spectrum PFM, which has been developed almost a decade ago, actually more than a decade ago. So the basic idea is that in the normal AFM, when we read the piezo response, we always have our DC signal on. So when we are trying to ramp the hysteresis loop, we ramp the DC, and in the meanwhile, we use the AC to read the piezo response. So people really want to look into if we don't have this kind of DC, because if you apply DC, you may expect some kind of electrostatic interactions involved into your piezo response. So the original idea is that can we actually read the piezo response without the involvement of the DC? So this gives you this kind of pulsed DC PFM, or the switching spectrum PFM later named. So the idea is actually quite simple. Instead of the directly ramp from the normal voltage, DC voltage we used in hysteresis loop ramping, we separate into several steps. So each step, I increase the DC a little bit. But after this step or pulse, I just remove this DC, just apply the AC signal to read the piezo response. And after the reading session, we do another writing session, or the on field, usually people call it, with a slightly higher DC. So in this way, we can still finish this kind of DC ramping, but now we can get both the on-field and off-field hysteresis loop. So by comparing the difference of these two hysteresis loops, we can actually derive a lot of information. For example, how much the polarization can actually be remained when we remove the DC, and actually whether there's kind of spontaneous or presentation rearrangement. And of course, we can also have a rough idea about what kind of electrostatic interactions contributed to the piezo response measurement we did. So this is the basic idea of the switching spectrum PFM. And we trying to move it further bit by introduce this kind of DC offset for the reading voltage. So as we mentioned many times, the electrostatic interaction can be a very important and almost unavailable artifacts in normal PFM measurements. So by introducing this reading DC offset into the switching spectrum PFM, we can actually compensate the CPD between the tip and the sample. And once you don't have this CPD, of course, you don't have any electrostatic interaction force, theoretically speaking. So this is a way to actually remove or completely screen out the electrostatic interaction involvement in the piezo response. Of course, from there, people develop further other modes called contact mode KPFM, which will be another topic. If you are interested, we can maybe have some individual discussion later on. But the general idea is that by doing this kind of swift of the DC offset together with the ramping of the DC writing voltage and performing this off-field reading, we can remove or separate the electrostatic interaction and the pure piezoelectric response. And that's the last slide for my presentation. Sorry, I dragged a bit longer than I expected. So I think we will have a short break, then we will start our virtual lab session. Is that right, Leah?
Hey, Jinyun. Hey, thanks a lot for the sections. Yes, you are right. I think we have we should start at 11:30 for the virtual demo sections. So we give all the audience and yourself a couple of minutes to either prepare the sections or have a bio break. So thanks everyone to stay with us so far, and we will have a few minutes break and then come back at 11:30 Kuala Lumpur or Singapore time. So see you later.
Okay, see you later.
Ready, so we can resume the sections and continue for the demonstration part. Hi, Chen Yun. Just let me know when you are ready. Dear audience, let's just give Dr. Chen a few minutes. I guess he is setting up some of the audio system. We're switching the gears. We should start shortly after this is resolved. Uh,
All right. I hope everyone have enough rest, get some water or something like that. Because in the previous session, I think it's quite intensive, a lot of things to memorize maybe. So the following, roughly about 30 minutes, we are going to have this kind of virtual demo. So I'm in my demo lab in Singapore right now. I hope you can all see my webcam together with the shared screen. Liang, can you confirm you can see both?
yes, Chen Yun, we can see one camera seeing the actual instruments, and the other one is a screen of the software.
It's my volume. Sorry, I mute my speaker earlier. So Liang, can you see both?
Yes, I can see both the AFM as well as the software.
Okay, great, thanks. So as you can see here, we have the dimension icon system here. We already mentioned earlier, for each AFM, you need the basic components, the scanner, like this one, and we have the tip. Of course, you cannot see right now, but from the software interface, from the camera view, you can see the beam-like cantilever right now, right under the red cross. And we have this big sample stage. You can put your sample on top of that. And this sample stage is actually conductive, which can be applied, the BIOS can be applied through the controller. And besides that, we also need optics. So it helps us to find the sample to direct the cantilever to the specific locations. So this is generate the basic components of AFM. And today here, we also attach a module here. This is a peak force tuner module used to measure the conductivity of the material. So on the system head here, we have specific connections to apply different kind of modules, like the peak force tuner module here, like our SSRM module and some other modules. And in the corner, if you can, I'm not sure whether you can see clearly or not, we also have a heating stage attached to it, which is something Dr. Chang mentioned earlier. So we can have the environment control during doing the AFM measurement. We can heat the sample up to 250 degrees, and which can be important in the polymer studies and some other material studies. So as you can see, the dimension icon is really a quite flexible platform. Basically, you can do almost all the AFM modes on this platform. So today I'm going to show you some example. Of course, it needs to be piezo response, otherwise off the topic today. So this is a very simple BFO film I have in my lab, and I already focus on the sample, so we are ready to engage. Let's start to have some image. So our software designed, the interface is designed in this way that you just follow this step-by-step workflow. And even for people fresh, new to AFM, you can still quite easy to understand the working flow here. And it's kind of error proven. You cannot, you want to do anything wrong. And we have a lot of safety warnings popping up if you, by any chance, mispress the button. So it's quite safe. And now it's already engaged onto the surface. So this surface is not very flat. I know nowadays some of the ceramic films can be really, really flat. And for 2D materials, it's of course even flatter. But this one is relatively tougher. Peak to valley is about 50 to 100 nanometers. So we are now in contact mode, which means we maintain the force on top of the cantilever during scanning the surface features. So in this mode, when you encounter something higher, the feature will push your cantilever upwards, which actually increase the deflection on the cantilever. So the controller will move the Z piezo upwards, or together with the together with the AFM cantilever. So in the image, we got some high features, and when we have some lower features or valley structures, actually deflection reduced on the cantilever, and the controller takes this feedback signal and move the Z downwards accordingly. Then it's reflected into a darker area or lower features in the topography image. So this is how the contact mode works, and the PFM is working on the contact mode to make sure that you have enough contact time between the tip and sample. Actually, that's kind of generally true for many electron modes. For example, when you're trying to measure the conductivity, you also want to keep the tip as long as possible to the sample to boost your signal. Although some other electron modes may not need this kind of long time contact, like when you're trying to measure the surface tension or work function, we use the KPFM. It's done to require this kind of long time contact. So back to the story. So earlier this morning, I write some features on this area, which is Dr. Chang mentioned, the domain writing, right? So on the BFO, when I apply opposite DC bounds at these two different regions, you will force the orientation of the grains or domains within these specific regions into a specific location. So when you apply opposite bounds, then the orientation will also be opposite, which means the phase will be plus minus 90 degrees difference. So now we are actually didn't apply any DC voltage, but just use AC voltage to scan, which PFM quite often calls reading. So we are trying to read this piezo response from these different areas. You can see once you get into this area, the phase is dominantly over minus 90 degrees. While in the neighboring area, which we didn't write, it's basically random. You have plus and minus 90 degrees phase descriptions. And move on to the center area where I write in opposite direction in a smaller area. Now you see within this smaller area, the majority of the domains actually it's plus 90 degrees in phase channel. So this is opposite to the neighboring area, evenly writing opposite DC voltage. So this is a very quick demonstration on how to perform the polling or the domain writing PFM. This maybe looks quite simple, but it's also quite straightforward way to test whether your sample is piezoelectric or not. So quite often, especially when people are talking about some 2D materials and also some conductive materials which they suspect they have the piezoelectric response. The very strong evidence to prove that is to see whether you can do the polling of such kind of material or not. So if you cannot do the polling on it, even if you detect some piezo responsive signal from such materials, very likely it's just other nanoelectric interactions involved or modulate or coupled into your piezo response signals. So this is about the polling. And we mentioned earlier that for piezo response, quite often it can be very weak. So we use a different method to try to boost the signal. The AC modulation is one way. It's the most common way to do it. And then now I'm going to change the frequency for this AC, and then you will observe the difference here. So you can directly see that amplitude channel gets much lower. That's because I changed from a frequency, a higher frequency, relatively close to the contact resonance frequency of this between this tip example to off resonance frequency, which is by now is 15 kilohertz. So at this low frequency, you still have some signals here. Of course, I need to change the parameter a little bit. For example, I need to lower the bandwidth a little bit because we are using a much lower frequency right now. So you can still see the grain distribution with different grains with different distributions within the materials. And if we change the scale of this one, we still see some piezo response, although it's quite weak. For now, it's about 10 picometers. You can still clearly see the grain distribution from the amplitude. And from there, you can see that at each grain, actually, the response can be different at the same off resonance frequency. And we also see from the phase channel, you have very distinguished orientation distribution, plus 90 degrees. Although it's noisy now, part of the reason is I opened the hood in order for you to see the footage, video footage from my webcam. So usually we will suggest doing this kind of measurement, close acoustic hood to screen out the environment noise. And also another part of the reason for this noise data is because now the amplitude is quite small. So even if we apply the locking amplifier to demodulate AC signal, if the amplitude itself is small or the noise signal to noise ratio is quite low, then the phase will not be very accurate. So that's why it's very useful to apply a frequency close to the contact resonance frequency of the current contact system. And as you saw earlier, the signal can be really boosted, and you have a much cleaner phase image here. So how can we determine the contact resonance frequency? So we can just do a quick sweep on top of the sample. For this material, basically we have piezo response almost everywhere. So no matter where you do the sweep, it's okay. So what we're interested in is the amplitude, because we're trying to find out the contact resonance frequency. And what we're trying to sweep in X direction, well, these, of course, quite obvious is frequency. Then we can determine in which range we are going to do the sweeping. For this one, I know roughly the resonance is close to 300 kilohertz. So I can narrow down this range here, change scale a little bit. Then you can see it's trying to sweep from 250 all the way up to 350. And we see the contact resonance peak at close to the 338 kilohertz. Of course, it's not necessary to really use a peak, even if at this kind of relative flat area, at the foot of this peak, you already boosted your signal quite a lot. So in literature, people are still arguing whether you should directly use a contact resonance frequency or you use frequency further bit away from the actual resonance frequency. So for different kind of applications, actually, you can choose which one to apply. So let's say I really want to boost my signal quite a lot. I move it very close to the peak location, somewhere here. And then let's come back to see the signal again. So now you see your amplitude boosted quite a lot. And your phase is much cleaner because your signal to noise ratio for the amplitude is much better, significantly improved. And the phase is actually derived as a locking amplifier based on amplitude data. So now you can see clearly see the distribution of grains in the phase channel, and somewhere you can also clearly see the domain walls. So this is the so-called contact resonance PFM. But I also mentioned earlier in the presentation, this contact resonance can shift during scanning. If you do a single spot, maybe it's okay. But if you are trying to scan image in the meanwhile doing this kind of PFM measurement, then depends on the contact, this frequency can be different. So in order to address this problem, we introduce DataCube contact resonance PFM, which can actually track the contact resonance at each pixel. So what we need to do is first determine in what kind of range this frequency may change. So here I'm just doing a quick sweep. Of the frequency, start from 200, give it a relatively wider range, 200 to 400, and increase drive amplitude a little bit, and want to turn signal here. Start. Now, you see, if I do a quick test, I can see that when I sweep from 200 kilohertz all the way up to 400 kilohertz, I have a peak around 320 or 320 to 330, somewhere in between. So you already see this peak changed from what we saw earlier, right? So that means within this 320 to 340 window, the frequency will change a little bit. So I can further narrow down this one, maybe from 300 to 380, narrow down a little bit. Yeah, so we can still cover this peak within this range, which is good. Slightly increase to make sure my peak is relatively in center. Okay, so once we've done this, we can move into the DataCube part. So I'm going to increase the resolution a little bit. And I still use this frequency range for my sweeping, and all the other parameters I don't have to care right now. So I want to see the contact contact resonance amplitude, which is amplitude as a contact resonance frequency, and maybe I can also check the frequency change. So now we are all set. We can start the scanning. So in the bottom window here, what you are seeing is that at each pixel, the AFM is trying to sweep the frequency, and based on this amplitude versus frequency plot, it's trying to fit this plot to find out the real contact resonance at each pixel. So the blue line is the raw data, which is amplitude versus frequency data, and the red line is the fitting line. So you see some oscillation, some noise, especially when I talk. Again, it's because of the enclosure is open, so the AFM is quite sensitive to the acoustic noise. So, but as you can see, the red line can always fit nicely onto the blue line, which means at each pixel, we can always pick up the right frequency, so that the amplitude you get at this specific pixel is always the strongest at the current drive amplitude. So this is a very nice way to make sure that even for a very weak piezo response material, you can still have a very clear image from the PFM. But the disadvantage, I wouldn't say disadvantage, more or less like the limitation is that when you're trying to do some quantitative measurements for the PFM characterization, the contact resonance application is still quite, will give you some extra difficulty in interpreting the data. So there are a lot of papers talking about this specific question, whether we can use the PFM amplitude observed at or close to the contact resonance to calculate the piezoelectric coefficient, or the D33 most commonly. So there are still some arguments there, but for the qualitative study of the piezo response material, this contact resonance method is really a good addition to your normal traditional PFM method. So as you can see, when we do the scanning, we of course have the topography, image of the sample. For the time concern, I only scan it at a relatively low resolution, which is 64 points per line and 64 lines per image. But still, we can see some grains because within this 5 micron range, these grains are relatively big. So even if I have relatively large pixel size, I can still resolve these grains. And from the amplitude channel, we can see that at each grain or at different locations of this sample, the piezo response is also slightly different, which we also mentioned earlier. It's not uniform, right? And also the frequency channel, you didn't see a big frequency change, but if you look into the scale here, it's about 70 kilohertz. So within this range, and also from the lifetime holding spectrum, you can see the frequency jumps quite a lot, all the way from maybe from 310 all the way up to 340 or something like that. So the range or the window is roughly about 30 kilohertz. If you don't use this kind of real-time tracking for the contact resonance, you can imagine that at each pixels, actually the response is boosted with different kind of enhancement factor. Because when we use a contact resonance, we basically take advantage of the Q factor or the quality factor of the cantilever to boost this piezo response. And if you at different location of the contact resonance peak, then the effective Q factor will be different, which means your data is not or are not actually normalized. So in order to make sure that you always compare apple to apple, you have to make sure that you are really with the same boosting factor, which actually what we are trying to do here. You always pick up the amplitude at a resonant frequency So you use a Q factor of your Kent level to boost your piezo response, and that makes it possible to actually compare the piezo response from location to location and from point to point, from grain to grain, from domain to domain. So this is a really apple-to-apple comparison. And that's also an important reason why we set up a separate mode called the DataCube content resonance PFM. So of course, for inside the DataCube, we have another mode just called the DataCube-PFM mode, which we are not going to ramp the frequency, but something else. For example, I want to see how the reading voltage affect my piezo response, or I want to see if I can play around the offset while I was doing the reading to see whether this affects my piezo response to, for example, to compensate the CPD, things like that. So in that workspace, you can do this kind of experiment. So yeah, I think that's more or less I want to show you for the demo session. It's not necessary to finish this image. I guess you already see what we can do with this kind of real-time tracking for the content resonance, and what kind of benefit you may get from such kind of technology. So I don't want to delay everyone for lunch, so I think we can move into the Q&A session. Liang, are you going to take over from here?
All right, thanks, Chen Yun. Thanks a lot for the great demonstration sections. It's pretty clear. So hopefully all the audience also get the same impressions. Well, we are pretty much on track in terms of timing. So I think it's time for us to at least spend some time to discuss some of the good questions that raised by the audience. I see numbers of questions are pretty much scientific, so let's start with those one first. There's one question is talk about that is clear that the influence of the grains and domain walls in the material has a strong connections with the subsequent growth of the nanomaterials, and it's also for its energy harvesting applications. So it's wondering how can we at least maybe or try to separate the influence of grains and domains from the deflection sensitivity of the nanorods during the PFM measurement. Since where the string is applied, the entire sample oscillations is in response to the applied field. So I'm not sure, Dr. Chang or Dr. Chen, who you feel it's have a good suggestions on this topic.
Dr. Chang, I think maybe you can try first.
Sorry, yeah, just okay. So the question is referred to as a newbie in PFM, how to differentiate the materials from PFM and then to measure using the PFM2 to measure the PFM. Am I right?
I think it's trying to see whether in the PFM whether we can separate the influence of the grain boundaries and domains in terms of the deflection sensitivity.
All right. Okay, thanks, Liang. Yes, in the PFM measurement, you will be able to see a very clear, distinct grain boundary and also the domains. So, for example, in the ceramic is a polycrystalline material. You have a number of grains that being bring together. So, in this case, you have a grain boundary. Well, it depends on the grain boundary, the size of your grain boundary. Because many articles reported that the grain boundary will have generate a region of different charges than your grain. So it basically able to distinct the grains and the grain boundary and the grain itself. For us, we did measure that. We are able to not only to use PFM to identify the distinct between grains and grain boundary, but we also further using CFM to further identify these two. I would say yes, it will be able to recognize or identify the grain boundaries and the grains as well.
Yeah, I agree. Thanks, Dr. Chang.
Thank
Jimmy,
you.
you have anything to add on to this topic?
Yes, so I think that it's especially for AFM in potential application in this field. So as Dr. Chang mentioned, we may see some strain distribution different at the boundary and the grain. And we also may see different kind of charge accumulation or charge density difference, which will give you different kind of surface potential when you're trying to measure with either EFM or KPFM. So I think one of the example I mentioned in my presentation is actually using KPFM together with PFM to observe not only the grain boundaries, but also the domain walls, what kind of difference is there. So actually you can differentiate, you can actually see the contrast in both modes. So this gives you an idea how actually physically these kind of things all combine together. So whether you can measure it with AFM or not largely depends on the dimension. So when the grain boundary is relatively wider than a few tenths of nanometers, of course we can do it. So I mentioned earlier the limitation or the extreme of our lateral resolution is basically directly related to the tip radius. So a few tenths of nanometer is no problem for AFM. But if your boundary is very, very tiny, then it can be challenging. So it depends on sample.
Yes, thanks, Yun, and thanks, Dr. Chang again. I see there's a few questions actually. If we put them together, is regarding Dr. Chang, as you mentioned in your presentation, that to get a good PFM data, we actually need to understand our sample. So I think the audience generously wants to know in which aspect of the sample that we really need to know, and also in terms of sample preparation, how sample preparation might actually affect the PFM data. Mind to shine some light on this area, Dr. Chang?
Yes. Okay. First, about the sample preparation. Okay. About the sample preparation. If let's say we refer to the thickness of the sample, you can actually. I don't think there is any issue with thin sample, thin film, nano. Which is in the nano dimension, nano particles, nano tubes. As long as your tip will be able to point to the area or the region that you are interested. So this is the first part. The second will be the thick sample. You can't have imagine you have a bulk sample, say for example a bulk single crystal or about ceramic. It can't be too thick because the signal that is being transferred from the tip to the sample and eventually to the bottom of the sample holder back to the lobe, to create a one feedback loop, the signal basically is rather weak. So if you are having a very, very thick sample, then you might actually have the challenge how you are able to control the signal from the top to the bottom and form a feedback loop. So this is a challenge. So I will actually advise you to thin down your sample. All right, you need to polish your sample, thin down your sample to typically maybe you have to actually play with it to see how strong the signal able to obtain the samples from the top to the bottom. But again, when you prepare your sample, you also have to be aware whether you wanted to polish the top or the bottom, right? So if you are polishing the top surface that you are going to measure when you put your tip on, you have to be aware that when you polish, you basically generate a strain onto the surface of your sample, and also you also might lose the morphology, the typical morphology that you might interested to observe. So you got to be very clear in what you want before you prepare your sample. So maybe you can actually prepare polish the bottom, because the bottom is in contact with the sample holder, which will be observed from the view of the atomic force microscopy topography measurement. And have I answered all the questions in terms of sample preparation? What else? What is the questions? The next questions? To getting excited.
Thanks, Dr. Chang. I think what I read here is that I think for many audience, they are still new to the PFM. So since we all understand that it's important to understand our sample before we start to prepare it and then mount it onto the AFM to run a test. So for the topic we say we need to understand our sample, do we have something specific to say that, okay, in this property of the sample we really need to know so that you can get a good sample preparation and the PFM data? I think there are some questions regarding this where the audience wants to know in terms of which aspect of the sample that we actually need to know before we think of how to prepare and measure the sample.
To me, if the sample is having is showing piezo and is showing either piezo or ferroelectric behavior, you should be able to measure you should be able to use PFM to measure, to obtain the data that you would like to see. The challenging part is how. It's actually the method, and also the selection of the tip also is challenging. It's a sort of a very high challenge requirement for you to go through this process. Of course, based on my experience, there's no for PFM2 you need to try. You need to try definitely for the first time to get a feel of the relation between your sample and the tip, conducting tip as well as the tool. And from there, you will know how you are going to, you will be move on from there. It is never one stone hit everything. That is impossible to have this. Yeah, so different material, different behavior, similar to the measurement tips, the tips that you are going to use as well. Because the other interesting part is you have to understand the tip that you are using has various kind of tip, various kind of conducting layer, and various type of stiffness. Because it depends on the stiffness, the K property of the tip to obtain and to interact with your sample. Yeah.
True. All right. Thanks, Dr. Chang. Actually, you have anything to add in this topic? I think it's because it's related to the sample preparation. So we Bruker probably also engage numbers of different type of samples when we do the sample tests and measurements and so on.
Yeah. So I will just talk about the sample test part. So of course, one thing, the first concern of the AFM sample is the roughness of the sample. So AFM is looking to the nanometer scale topography and the nanoelectrical, nanomechanical properties. So the roughness cannot be too high. So if your sample is quite rough, then it can be an issue. So as Dr. Chang suggests, you can think about whether do the polishing or do some annealing or as a kind of a treatment to trying to reduce the surface roughness. If you have this kind of tens or hundreds of micrometer scales features on your sample, of course we cannot scan. You cannot even land your AFM tip onto this kind of very rough surface. So that's a general requirement for the AFM sample preparation, not only for PFM. The second thing is that you need to make sure that we can find a way to properly channel the BIOS through the sample. So one concern is the thickness of the sample. And another concern is what kind of substrate you use and how to attach your sample to the substrate to make sure that you have a good conductivity through it. And the third thing is also related to the thickness, but it depends on whether you want to see the polling effect or trying to do the dynamic piezoelectric spectra or not, or just want to see the piezo response from imaging. So if you are trying to do some polling or writing or switching, then you need to make sure that the film is thin enough, which the voltage from AFM can actually turn over. So if you have a rough idea about D33 or G33 of the material, then you will have a better estimation about how thick the film can be and how strong or how big the BIOS is required. So for the default settings, we can apply minus 10 volts of the BIOS for the polling experiment. Of course, we also have the high voltage options, which can apply up to 600 volts. But if you have the film is too thick, then even these hundreds of volts cannot be enough to turn it over. Then, of course, we cannot do the polling on such kind of samples with AFM. So these are all the concerns. And the last part, I think in actual experiment, Dr. Chang also have quite a lot of experience with experimenting different kinds of tips. So whether you use a longer tip or shorter tip, whether you use a stiffer tip or flexible tip, there's no general guidelines. It's really depends on which kind of sample and which kind of modes you are going to use. In general, I mean, if you use a shorter cantilever, then the piezo response will be relatively stronger because your diffraction sensitivity is higher. But shorter cantilever quite often means it's also slightly stiffer. So for some application, it may not be good, especially if your sample is soft, like I mentioned earlier. For some biomedical application for piezo materials, sample is relatively softer. If you use a too stiff cantilever, then basically you cannot do the imaging. Don't mention about the PFM. So in this way, you have to find something maybe less stiff or more flexible, but still have a relatively good signal to noise ratio for PFM detect, things like that. So this really a lot of factors affecting whether you can get a nice PFM image or not, or whether you can have a nice butterfly curve or not. So we are still, for myself, I'm still learning during my sample test or demo sessions, all these kind of things. Every time I'm trying to accumulate some knowledge. I think that's a normal learning curve for most of people doing these kind of things. So yeah, I think that's more or less what I want to comment.
Yes, thanks, Dr. Chen, and thanks, Dr. Chang, as well, to answer these questions. I think there are still a few questions where probably due to the time limitations, we can't discuss in details. We probably can reach out to you to answer or discuss those questions to you separately. So as such, it's my turn to conclude this webinar. Thanks everyone for spending your time this morning to join this webinar, especially for the two speakers, Dr. Chang and Dr. Chen, to share with this comprehensive presentation slides with every audience here today. It is unfortunate that due to the current pandemic situation where we can't really see each other face to face, but I think in due course, we do want to work together with Dr. Chang and the Monash University to really actually host a seminar sections or workshop sections where we can invite all you to come and we can sit down together to discuss all kind of interesting research topics together in due course. Well, as such, that's conclude our webinar and online demo today. We hope you all find the information is informative and helpful. If you do have further questions and clarifications, please feel free to reach out to either Cowen Tan from Quest Nano Solutions as your local contact, or email Bruker at bns.asia@bruker.com. And once again, thank you everyone, and have a nice day ahead. Thanks a lot. Bye-bye.
Thank you very much. Have a nice day.
Thank you. Bye-bye.
Thank you. Bye-bye.